Hello everyone, welcome back to another MCR3U1 video, and we are carrying on with chapter 5, and today we will be evaluating trigonometric ratios for angles between 0 and 360 degrees. We have already started this concept in the last video, but we will solidify our understanding further right now. After the video, you may find extra practice questions for sections 5.4 on pages 299 to 301. There's also a mid-chapter review on pages 302 to 304 that covers basically everything we've done so far up to this point, including today's lectures. So you can take a look at that if you want even more practice, and let's get started on the lesson. Here is the success criteria for today's lesson. We want to use the coordinates in a Cartesian plane to express trigonometric ratios, so we'll get an understanding more why we sometimes use negative x and negative y values for the length of the triangles we create in the Cartesian plane, like we did in the last few videos. Next, we want to learn the CAS rule, which I have mentioned a lot in the past couple videos, which will make it really easy for us to solve for trigonometric ratios in different quadrants. And lastly, we want to use the related acute angle, which we learned in the last theory video, to solve for trigonometric ratios at the principal angle, which we have somewhat also covered in the past lecture. Okay, so let's go. First, let's go over how we use coordinates to solve for trigonometric ratios. If we take a look at our Cartesian plane here on the left, we can see that we have graphed a point P right here that is located at x and y on our Cartesian plane. From this point, we can create a right angle triangle with sides y, x, and r. And as we can see here, as we have done in the past few videos, right? We're creating a right angle triangle right in the Cartesian plane. One side of this triangle is our initial arm, which is here, which is not always the case, but since we're in quadrant 1, it's our initial arm, and I'll explain the other scenarios in later slides. But in this case, one side of our triangle is the initial arm. The hypotenuse will be our terminal arm, the hypotenuse of the triangle. And our last side will be this side here, side y, right? And between the terminal and the initial arm, we have angle theta, right? We can also see here on the left that since we have a right angle triangle, we can use Pythagorean theorem to solve for r, just given our point P. So we can use this equation, and we can get r by r squared equals x squared plus y squared. So if we're given a point P, and we draw our right angle triangle, we know what x is. We know the length of x is our x coordinate. We know the length of y is our y coordinate. And if we put into Pythagorean theorem, we can get r. We can get the hypotenuse of a triangle. From this point, we can actually express our 6 trigonometric ratios, which are displayed here on the right. So I'll go through them. We have sine of theta. So sine of theta is going to be opposite over hypotenuse. So we have opposite, and our hypotenuse is r. So we have y over r. We have cos theta, which is adjacent over r. So adjacent to theta, we have x, and hypotenuse is r, of course. We have tan theta, which is opposite over adjacent. So opposite, adjacent, we have y over r. And then we have our reciprocal trigonometric ratio. So cosecant of theta is going to be the reciprocal of sine of theta. So if we have y over r here, we're going to flip it, and we're going to get r over y here for cosecant. Secant theta, again, reciprocal of cosine. So we're going to have r over x. And cotangent, again, reciprocal of tangent. So we're going to have x over y, right? Adjacent over opposite this time. And if our terminal arm is in another quadrant, right, unlike here, some of our ratios can change signs from positive to negative, because if we are in any of the other quadrants other than the first one, our x coordinate or y coordinate could be negative, which will result in some negative ratios, right? These ratios will always be the same variables, like sine theta will always be y over r, but sometimes this y coordinate will be negative, or sometimes our cosine may be negative because this x could be negative, right? Which we'll go over in the next couple slides. But just note that the sign depends on the sign of the ratio depends on the quadrant, right? Because it depends on x and y and if they're positive or negative. Okay, so let's keep going. Let's look at the special cases we want to watch out for. The first special case is when the principal angle, so theta, is 90 degrees. And here, our y value will be 1, our x value will be 0, and our r value will be 1, right? Because if we have up here, like in the last slide, let me make it better, right? Here's our Cartesian plane, our x and y coordinates, right? If we have our point P, x and y, and we have our terminal arm, our initial arm, here's our triangle, here's our angle theta, right? If this angle theta kind of continues until we hit 90, this side of our triangle is going to get smaller and smaller and smaller and smaller until it gets to 0. So that's why our x, this value of the length of the triangle, it's going to be 0, because as this angle increases, this side is going to contract until it hits 0, until we hit the y-axis, right? And this side, and this side is going to increase, but we just say it's 1 just to keep our ratios nice and clean. This side could be larger, right? But for just to make our ratios look cleaner, we keep it as 1. We keep all the sides as 1 or 0. So here, our y value is going to be 1. Pretend this right here is like this triangle kind of squished to the left, right? So our y side, right, is going to kind of keep going left and left and left until we hit the y-axis. And that will actually make it the same length as our hypotenuse, right? Because pretend we're squishing this triangle, we have a hand right here, and we're pushing this triangle this way, and it's kind of like squishing to the left. And once we hit the x-axis, our y side is going to be the same length as our r side, and we just say that they have a length of 1, so we can write our ratios, right? So if we have a length of 1 here for our y-coordinate and a length of 1 for our hypotenuse, which is r, now we can give our primary ratios. Sine theta is y over r, like we saw in the last slide. So that's going to give us 1 over 1, which is 1. Cos theta is going to be x over r. R, we know it's 1, but x, again, this side right here is going to kind of squish left until it hits 0, until its size is 0, until its length is 0. So we're going to have 0 over 1. It's going to give us 0 for cos theta. And for tan theta, we're going to have y over x. And we know y is 1, x is 0. So we're going to get 1 over 0, which is undefined. So our tan of theta is going to be undefined. Now, next, we'll look at the case when our principal angle is 80 degrees. And in this case, our y value is 0. Our x value is negative 1, right? Because we're going in the negative x direction. And our r value is also 1. So if we have, instead of this triangle in the first quadrant, we have it in the second quadrant, right? We have our initial arm here, our terminal arm here, right? We have this triangle here, and we have this principal angle theta. As this principal angle keeps going to 180, right, it's going to push this triangle down from here, right? This side is going to get shorter, right? Our y side is going to get shorter and shorter until it hits 0. And once the triangle is at the x-axis, our hypotenuse here, our hypotenuse is going to be the same length as our x length, right? So our x and our r are going to be the same length, but r, remember, is always positive because it's hypotenuse, and it's defined as r squared equals x squared plus y squared, so we're going to get a positive number. But x, we're going in the negative x axis direction, So our x value is going to be negative, it's going to give us -1, right? And our r value is going to be 1. So sine of theta, y over r, we have 0, right? Our y value here is 0 as it decreases all the way to the x-axis. 0 over 1 is going to give us 0. We have x, cos theta equals x over r, which is the same thing as saying -1 over 1, right? Remember, our x is -1. So cos theta is going to give us -1. Tan theta, we have 0 over -1, which is going to give us 0. Okay. Next, we have theta equals 270. And in this case, y is going to be -1, x will be 0, and r will be 1, right? Because now let's draw it in the third quadrant, right? We have something like this. Here's our triangle, and we have our principal angle going all the way here. Now, as our principal angle grows and grows until 270, which is this line down here, our x length is going to get shorter and shorter and shorter until we hit the y-axis, and then our x length is going to be 0. Our y length is going to get larger and larger as we push this triangle kind of to the right, and once we're at the y-axis, the y length and the hypotenuse, right? This is our y length, and our hypotenuse are going to be the same down here, right? It's like a squished up triangle. That's how you want to think about it. So our y value, since we're going down in the negative y direction, our y value is going to be -1, our r is still going to be 1, and our x is going to be 0, because we squished it all the way to 0. We squished this length all the way to the right to 0. So sine of theta, we have y over r, so -1 over 1 is going to give us -1. Cos theta equals x over r, 0 over 1 is going to give us 0. And then tan theta, we have y over x, and y we know is -1. X is 0, so we're going to get -1 over 0, which is undefined. So tan of 270 is going to be undefined. And lastly, we have the principal angle being 0 or 360 degrees. And you can pick either one because both of these angles begin and end on the same line, which is the positive x-axis, right? So for 360, it goes all the way around, right, to 360 degrees. And for 0, we just don't move. We just stay right there. So our x value here would be 1. Our y value would be 0, and our r value would still be 1. So our r value, as you can notice, is 1 every time. But now, let's redraw it here. Right? We have this triangle down here. Here's our terminal arm. We make a little triangle, right? As we push this triangle up now, we squish it up. This length, the y length, is going to get shorter and shorter until we hit the x-axis, and then it's going to hit 0. And as we push the triangle up, our hypotenuse is going to become the same length as our x length. And our x length, in this case, is going to be positive because we're going in the positive x direction. So our ratio of r, sine of theta, is going to be y over r, which is 0 over 1, which is going to give us 0. Then cos theta, we have x over r, which is going to give us 1 because x is 1 and r is 1, so 1 over 1 is going to give us 1. And tan theta, we have y over x, which is 0 over 1, it's going to give us 0. Okay? So those are our special cases that we kind of want to memorize, right, in case we get it in a question. So we know that if we get sine of 90, right, of course we can put it into our calculator, but if we can do it mentally, we can further strengthen our skills and we can just be much faster as well. So sine of 90, if we get it, we know it's 1. If we get, let's say, cos of 270, we know it's going to be 0, right? And these are just the cases that we just really want to know well. Now let's move on and look at the CAST rule, or the CAST rule. As we know, the terminal arm, the direction the terminal arm points to determines the sign of x and y. And as we can read up here, since r, the hypotenuse, is always positive, right? The primary and reciprocal ratios depend on x and y. The signs before these ratios depend on x and y. And so the CAST rule is something we can quickly memorize, so we don't have to really see if x or y are positive or negative every time we do a question, right? So how does the CAST rule work? Well, we start in the fourth quadrant, and we spell CAST going counterclockwise, placing a letter in each single quadrant, right? Each letter of CAS, C, A, S, or T. The letter represents what primary trigonomic ratio is positive in that quadrant. Remember, positive, not negative. So in quadrant 1, we have an A, which means that all primary ratios, A stands for all primary ratios will be positive in this quadrant, which makes sense because X and Y are both positive in this quadrant. So if we draw our little triangle, if we remember, here we have the Y side and the X side, and we're going in the positive X direction and we're going up in the positive Y direction. So and since R is always positive, all our ratios between X, Y, or R are going to be positive, right? Because we're always going to have positive number over positive number. So in quadrant number 1, every single ratio is positive. So sine, cosine, and tangent and their reciprocals are all positive. Okay. Next, in quadrant 2, we have an S, which means that the sine ratio will be positive in this quadrant, the sine ratio. And both the other primary ratios will be negative. So cosine and tangent will be negative in the second quadrant. And again, we can show this using X and Y, right? If we have a triangle, that's a really bad triangle, right? And our angle, our principal angle goes all the way here from initial arm to terminal arm. And we have positive Y, but then we have a negative X because we're going in the negative X direction, right? And R, so our sine of theta is going to be Y over R, which is going to be positive, but then our cos of theta is going to be negative X over R, that's going to be negative, and tan of theta is going to be Y over negative X, which is also going to be negative. So in quadrant number 2, you can see here, only our sine is positive, our sine ratio, right? And next, okay, I'll explain the reciprocal ratios at the end, but let's just carry on. Then in quadrant 3, the T stands for tangent, which means only tangent is positive in quadrant 3, which also makes sense because X and Y will be negative in this quadrant, so they will cancel out the negatives when we do the tan ratio, right? So in this quadrant, only tangent will be positive and all other ratios are going to be negative. So quadrant 2, so now in quadrant 3, only tangent will be positive. And finally, we have C in quadrant 4, which tells us that only cosine will be positive in quadrant 4, which I'll put up here. And sine and tangent will both be negative. And again, it makes sense because X is positive and Y is negative in this quadrant. Once you do all the ratios, you'll get a positive cosine ratio, but a negative sine or tangent ratio. So now that we know the CAS rule, all we really need to remember is what letter goes in each quadrant. And when we are given the principal angle and we find the related acute angle, we know that sine, cos, or tangent of, I'll just use sine as an example, but you could use sine, cos, or tangent of the principal angle will equal positive or minus, positive or negative, of sine, cosine, or tangent of the related acute angle in each quadrant, right? So now that we know this CAS rule, we just need to remember what quadrant we're in, what ratio we're using, and remember if in that quadrant that ratio will be positive or negative. And then we know exactly what the sign is. We don't have to draw to really see our triangle and if X and Y are negative, and see if we need to choose a negative sign or a positive sign. We just need to remember the CAS rule. So for example, if we are in quadrant 3, here's our terminal arm, and we have an angle that's over 180, let's say 200 degrees, right? We're going past 180 by 20 degrees, so our related acute angle is 20, right? So now we are in the third quadrant, and let's say we're using the cosine ratio, right? It's asking you to determine what is cos of 200 degrees. Well, that is going to equal plus or minus cosine of the related acute angle, which is 20 degrees. And how do we know if it's positive or negative? We use the CAS rule. So since we're in the third quadrant and we're using cosine, we know that in the third quadrant, since there's a T, only tangent will be positive in this quadrant. So it's going to be negative cos of 20, right? As you can see, it makes it very, very easy for us to determine if it's positive or negative ratios, right? Now, exactly. So that's pretty much it for the CAS rule. Now that we have learned the CAS rule, let's go over how we can use it when we have a point P in the third quadrant, for example. We want to again draw our right angle triangle as we have here, and making the side length x and y. Okay, we're keeping them positive for now, but we know that these may change because we're in different quadrants. And r, of course, will be our hypotenuse. Which we can find by using again the Pythagorean theorem. R squared equals x squared plus y squared. And then we have our principal angle going from the initial arm to the terminal arm, which is also our hypotenuse. Our terminal arm is our hypotenuse. Okay. Now to find the ratios of our principal angle theta, we need to find the ratios of our related acute angle beta, and then simply place a positive or negative sign in front of our ratio, depending what quadrant we're in. So if we look here on the right, our first ratio is sine, right? Let's say we find sine of beta, which is going to be y over z, right? Sine of beta is going to be opposite over hypotenuse, y over r, still keeping it positive. And as we know from before, the sine of the principal angle here equals plus or minus the sine of our related acute angle. But now, and of course, since we just found out what sine of beta is, we can just substitute the sine of beta by a y over r, but we still need to figure out if it's plus or minus. This is where the CAS rule comes in. If we don't have the quadrants memorized, we can, of course, draw each letter. Cast. Remember, we start in the fourth quadrant, and we spell cast, going counterclockwise. Once we do that, we can see that we're in the T quadrant, the third quadrant, right? Meaning that the tangent ratio will be positive in this quadrant. That also means that the sine and cosine ratios will be negative in this quadrant, which means that sine of our principal angle, it's gonna be negative sine of our beta. So sine of our principal angle is gonna be negative y over r. In this case, because we are in the third quadrant. With cosine, it's pretty much the same thing. We can find cosine beta, and it's, remember, adjacent over hypotenuse, so x over r. Again, keeping everything positive, because then we can find the sine through our CAS rule. So we find cosine beta, which is x over r, and then we are in the T quadrant, so cosine of theta again will be negative cosine of beta, as cosine is negative in this quadrant. So our cosine of beta is going to be equal to plus or minus cosine of beta. We found out cosine of beta is x over r, so we substitute in x over r for cosine beta, and we know we're in the third quadrant, so it's going to be a negative sign in this case. Negative x over r will be our cosine ratio over principal angle. Okay? And last primary trig ratio we have is tangent, which we know is positive in quadrant 3, so because we have the t there, so tan of theta will be equal to tan of beta. So we find out tan of beta, opposite over adjacent, right? Y over x, is it plus or minus? Well, we know that we're in the third quadrant, there's a t, so we're gonna say tan of principal angle equals plus or minus tan of related acute angle. Tan of beta we know is y over x, so we substitute that in, and then we find out through the CAS rule that this is supposed to be a plus sign. Okay? Now, for the reciprocal trigonometric ratios, their signs depend on the sign of their reciprocal primary ratios, right? So since cosecant is the reciprocal of sine, and sine will be sine will be negative in quadrant 3, as we found out here, cosecant will be negative in quadrant 3. Same with secant, right? Since cosine is negative in quadrant 3, as we found out up here, secant will also be negative in quadrant 3. And lastly, since tangent now we're working with cotangent. Since tangent is positive in quadrant 3, which we found out up here, cotangent will also be positive, right? So if we want to find out the signs for the reciprocal ratios, we just have to find out the sign for their primary ratio that corresponds to it. The reasoning for the alike signs between reciprocal ratio is because the definition of a reciprocal trigonometric ratio is 1 over the corresponding primary trigonometric ratio. And since we are just flipping the numerator and denominator of the ratio, the sign will stay the same. So if we take cosecant as an example, right here, cosecant of theta will just equal 1 over sine of theta, right? And if sine of theta, if we substitute sine of theta in, which will be 1 over negative y over r, which will be the same as r over negative y. And again, it is the reciprocal, but we keep the negative sign, right? The sign doesn't change at all. So the sign of our reciprocal ratio will be the sign of our primary ratio. That's the reasoning behind it. It's just, we just flipping the numerator and denominator, but signs don't really change. And that is it for section 5.4, at least for the theory part. And in the next video, we will cover some examples regarding the CAS rule and evaluating trigonometric ratios with angles from 0 to 360 degrees.